Everyone, this is a quick video to show you the incredible, awesome power of logarithmic differentiation to make life a little easier. So this is maybe a bit contrived, but here's a strange function, fairly complicated, lots of exponential things going on, and I've restricted the domain here to be just positive values. We could maybe imagine this is, gosh, maybe a pandemic outbreak, and the CDC wants to know what the rate of infection decrease is at this period of 4 months in, say. So we would like to know that instantaneous rate of change right at that given point there, 4, 1.5. So how might we do that? Well, the old school method would be to look at the product rule, and it would be the derivative of these three things being multiplied. This constant we can kind of ignore and bring in at the end if we want to. So it'd be these three variable functions. Be the first times the derivative of the second part, which is these two. And then the derivative of these two would be another product rule. So it'd be the first times the derivative of the second, plus the second times the derivative of the first. And then when I've completed that first leg, I take these two things times the derivative of that first thing. So this is what it looks like right here, all broken up into that double product rule. And then after I did that, I could then substitute in place of x a 4. And I could then try to just start doing the calculation. And you see, you have got e to a negative 12, which is going to be extraordinarily small, but we're also multiplying it by something that's raised to, in this case, it'll be 2 times, 4 to the 4th times 9. And so there's kind of a lot going on here, and it's not immediately obvious what simplifications I can do and retain some accuracy. So even trying to do one more step here, you can see that it just gets really complicated. So there is a new way to do it that doesn't involve grinding out something awful like that. The new way is with logarithmic differentiation. And the key idea is just this, that if we take the log of a thing, and then if we have the derivative of the log, which is going to be 1 over x, if we have y equals ln of x, we can then use the laws of logarithms to untangle these things and then take the derivative and make it a little bit easier. So a quick review of the laws of logarithms here. They're analogous to the exponential laws. If we have a log and we've got the product of two things, we can separate them as the sum of their individual logs. So probably you know these already, but you should review them because they're absolutely essential to doing this correctly. But what we do is we go back to our function, and this is the original function, and I just think, just for simplicity's sake, I'm going to put this x plus 5 to the 7th on top of 5,000. Then when I apply the dividing rule for laws of logarithms, it's going to be the log of the first minus the log of the second. And then here's just two products, so I just add, that's a little extra plus sign there I don't need, plus the log of this, plus the log of that. So these four things really that are being multiplied, or multiplied, divided, and then multiplied by two things, they just get broken down into addition and subtraction, and that's really the breakthrough moment. Now, we do take the log of both sides, so when I take and do the derivative, before I even get there, I am going to do a little bit more with my laws of logarithms. Any exponent can be brought out front. That's why the 7 is right there. This is just a number, the ln of 5,000. This negative 3 is an exponent, so that negative 3 comes out. And this 4 is an exponent, so that 4 comes out. Now, one further simplification is that perhaps you've noticed that the ln of e is one of our identities, going back to our rules here, that the log base a of a is actually not in here, but the log base a of x to the a is going to be minus a. The log base a of a is always 1. All right? So then, going back to this, the log base e right here of e is 1, so that becomes just 3x. Now I can take the derivative. Taking the derivative of the ln of y, it becomes 1 over y, but don't forget the chain rule. We do not have this as a function of x, so I need to use my chain rule and say that the derivative of y is just y prime. Then the derivative here, whatever the ln is being taken of, goes in the denominator. That 7 just stays there and multiplies. The derivative of the ln of 5,000 is just 0, because that is just a number. Whatever it is, it does not change. The derivative is 0. The derivative of 3x, whoops, is not 3x, it is 3. And then the derivative of 4 times the ln of x is 4 over. The derivative of the ln is just 1 over x. So there we go. This is not too bad then, because now I've got it much, much simpler. I can substitute in 4, and then I can multiply both sides by y to get rid of that 1 over y. So there's my y that's appearing when I multiply, and I can plug in my 4, and I wind up with 7 over 9 minus 3 plus 1 is negative 2. And then I've got my 1.5. I just convert this into fractions because I don't need no stinking calculator to do this. I get negative 11/9 times 3 halves gives me negative 33/18. That is the slope of my tangent line. Slope of my tangent line is negative 33/18. If I go back to this graph and type that all in quickly, there it is, and there's my tangent line coming in with that slope of negative 33/18. What a savings in time. What a great invention. Good luck, everybody.